In this lab, we'll talk about converting circuit schematics to a physical circuit using a solderless breadboard and applying constant voltages using the analog discovery. Designing, analyzing, and building an electrical circuit usually begins with what is called a circuit schematic. A schematic is a stylized representation of an actual physical system. This is a schematic of our circuit. A schematic is a road map that describes the physical system. It shows the components, how they're interconnected, and it defines important variables and their sign conventions. Usually, variables and sign conventions used in analysis are also defined on the circuit schematic. We're just concerned with building this circuit, so I don't need to define any variables. The circuit contains three elements: a 5-volt voltage source that provides power, a resistor to limit the current, and an LED that lights up when current passes through it. Generally speaking, resistors are used to control current flow or provide a desired voltage difference. This is the circuit symbol for a resistor. This is what the resistors we'll use in our circuit look like. They have two terminals, and it doesn't matter how these terminals are oriented. You can swap them end for end without affecting the resistor behavior. The resistors have a set of colored bands on them. These bands provide a code that gives the resistance value of the resistor. I'll talk about reading color codes later. The 100 ohm resistor we'll use in this lab has bands that are colored brown, black, brown. This is the circuit symbol for a lighting emitting diode, or LED. This is a picture of the LED itself. The LEDs light up when you flow current through them, but the current has to be flowing in the correct direction, into the anode and out of the cathode. This means that LEDs are polarized or directional, so when building a circuit you have to insert them correctly into the breadboard, and you need to be able to identify the anode and the cathode. We'll use the lengths of the LED wires to identify the anode and cathode. The anode has a longer wire than the cathode. The next step in converting a schematic to a physical circuit is to identify the circuit nodes on the schematic. Nodes are simply points on the schematic where two or more elements are interconnected. However, wires, or perfect conductors, don't really count as circuit elements since they don't introduce any voltage differences in the circuit. In more official terms, a node is defined as a point that has a single unique voltage. There are no voltage differences inside a node. Since perfect conductors don't introduce voltage differences, we can put them inside nodes. Identifying nodes is a fundamental step in being able to assemble a circuit from a schematic. We identify nodes in the schematic and the breadboard, and then connect the components in the schematic to the corresponding nodes on the breadboard. These are the nodes I've identified in this circuit. The letters I've assigned to them are arbitrary. Node A connects the positive terminal of the 5-volt source to one of the terminals of the resistor. Node B connects the other terminal of the resistor to the anode of the LED. And node C connects the cathode of the LED to the negative terminal of the 5-volt source. Now we need to identify where the nodes on our schematic will be on the breadboard. To do this, we need to understand how the holes in a breadboard are connected. A typical breadboard is a large white plastic component with rows of holes in it. Each row will consist of 5 or 6 holes, which are electrically connected. Each row is electrically isolated from any other row of holes on the breadboard. Breadboards generally have one or more channels on them. The rows on either side of the channel will be isolated from one another. Since there's no voltage difference between the holes in a single row, each row of holes on the breadboard can constitute a node in a circuit. Exceptions are columns of holes that have a red or a blue line next to them. Now let's take a look at these concepts in the context of a real breadboard. This is a typical small breadboard. These 5 holes are electrically connected to one another, as are these 5 holes and these 5 holes. Any 2 rows are isolated from one another. This includes the rows of holes on either side of this central channel. So this row of holes is electrically isolated from the row of holes directly across the channel from it. The terminals of electrical components, for example this resistor, can be easily pushed into the breadboard holes. This allows us to use the breadboard to quickly interconnect circuit elements in order to create electrical circuits. For example, if I want to connect a second resistor to this terminal of the first resistor, I simply insert a terminal of the second resistor into any hole in the same row as the terminal I want to connect it to. Now, these two terminals are connected. These two terminals are isolated from one another. If it's convenient, I can use jumper wires, just pieces of wire that have the right diameter to fit into a breadboard hole, to directly connect two rows of holes. For example, if I place a jumper wire between these two rows, both rows are now electrically connected and they constitute a single circuit node. Many breadboards will have what are called bus strips running along the entire length of the breadboard. Each bus strip will generally have either a blue or a red line next to it. All of the holes in each bus strip are electrically connected. These strips can make it easy to connect the same voltage to multiple nodes. This is used mostly in larger circuits. Now let's use a breadboard to implement this circuit. To do this, we just need to assign rows of holes on the breadboard corresponding to the nodes on our circuit. Then we insert the terminals of our components into the holes on the breadboard that correspond to the nodes that the component terminals interconnect. I'm arbitrarily selecting this row of holes as node A, this as node B, and this row of holes as node C. Now, node A connects the positive terminal of the 5-volt source to one of the terminals of the resistor. Node B connects the other resistor terminal to the anode of the LED. And node C connects the cathode of the LED to the negative terminal of the 5-volt source. This is the equipment we'll use to create our circuit and apply power to it. The instrument consists of a typical breadboard and a power supply module that provides constant voltage levels of either 5 volts or 3.3 volts. To connect the power supply to the breadboard, simply plug it in to one end of the breadboard. The power supply is connected to a 5-volt USB port with this USB cord. Just plug one end of the cord into the power supply module, and the other end plugs into a 5-volt port on your personal computer or a power converter that provides 5 volts. To turn power on, press this button. A green light should light up. The final step is to set the power levels provided to the bus strips, these lines of holes with the red and blue stripes next to them. With the power module in this position, with the USB port pointing away from the breadboard, the blue bus strip will always be grounded. It will have a voltage of 0 volts. The red power strip, here and here, can be set to either 5 volts, 3.3 volts, or 0 volts, depending on the positions of these jumpers. With the jumper connecting the two central pins, there is no voltage difference between the red and the blue stripes. If I move it to this position, the voltage on the red stripe is 5 volts higher than the voltage on the blue stripe. With the jumper on the outer position, the voltage on the red stripe is 3.3 volts higher than the voltage on the blue stripe. We want to apply 5 volts, so place the jumper in this position. Our circuit requires a 100 ohm resistor. I can place that in the breadboard by placing the leads in 2 holes in different rows of the breadboard. To connect the LED to the resistor, place the anode of the LED at one of the resistor terminals. Now to apply 5 volts to this terminal of the resistor, I'll connect that terminal to the red strip And to apply 0 volts to the cathode of the LED, I connect that to the blue strip. The LED lights up. So this circuit seems to work. Getting the circuit to seem to work isn't really good enough for engineering though. We'll generally need to measure voltages and currents to make sure it works the way we want it to. One common instrument to make electrical measurements is a digital multimeter, or DMM. The use of the DMM will be a topic of a separate tutorial video.